Okay. Okay. I've known Gerald Ratzer for quite a number of years, initially through the Oxford and Cambridge Alumni Association, which meets once a month at the faculty club. So I have a little bit of background on him, and I've heard some of his comments in the past on climate. Gerald was born in England, but educated in Scotland and went to Glasgow University, where he did 4 years of honours physics. He started his graduate studies at Cambridge and was awarded an IBM fellowship to McGill. This made him the first graduate student in computer science at McGill all the way back in 1964. After that, he was appointed to a professional tenure track position at the age of 24. Apart from teaching and research, he consulted to several companies, including Hydro-Quebec. After early retirement in 2005 and promotion to Professor Emeritus, he switched his research to climate science and is now the most read member of his department. His presentation on climate may surprise you as he looks at data from a slightly different perspective. Gerald, over to you.
Okay, thank you, Rod. Really appreciate the introduction. So that's the first slide, and I promised to get through them in 30 minutes. I have to give credit to the co-author and the lead author of the work we've been doing. We've worked together with Doug Lightfoot for over 5 years, and we've produced 6 peer-reviewed papers. If there are
sorry,
any...
Gerald, before you keep going, or should we be seeing a slide right now?
Yes, I can see the first slide on my screen.
Okay, so I don't think we can see it. So if you have to share it.
Okay, just a second. I thought I'd shared already.
That's good, Gerald.
Okay, you've got that now? Okay, so I did mention Doug Lightfoot, but he really does all the hard work. And given our combined ages, which is getting close to 90, I think it's amazing that we've managed to do this for so long. Anyway, I hope everybody has a copy of the slide handout. And if you don't, you can get a copy from Heather or myself, okay? So the overview has to start off by saying this is the weather is a very, very complex system. And to try and make it available to people in the Rotary Club, I'm trying to reduce the science down to a few items. And the thing that I said is what can be reliably measured. Everybody usually talks about temperature, but there's lots of other variables so far as the weather and the climate is concerned. Things like rainfall, snowfall, how deep is the snow, and how accurately are these various data items measured. I'm just going to talk about 2 items, which is basically the sun and the oceans. And I think these are the most important factors along with the clouds. I will show you some historical records going back hundreds and thousands of years. And the idea which I'd like you to keep in mind is something detectable? Because there are activities going on, which if I had to ask anybody on this session, what's going to be the increase from from CO2? We argue that that increase measured in degrees centigrade is so small that it's not actually possible to measure it. And the even harder item is how do you attribute a particular event to a particular cause. So it's the cause and effect issue. And just because 2 things are correlated doesn't mean they agree. If they're uncorrelated, then that's an important fact. The scientific method you will have heard about, you have an idea, a model, a hypothesis, a concept, and unless you test it with real data, you can't be sure. And The famous person who worked in this area is called Richard Feynman, and he says, if you do a projection into the future and it turns out that it doesn't agree with real data, you're wrong. It's exactly what he said. And along with that, I have trouble with critical thinking in that I get a huge amount of data across my screen, and to know what's real and what's not real, it's difficult. And I'm going to ask you to do a little bit of critical thinking on this slideshow. So I'm going to start with the sun, which I think is the most important item. This is a brand new photograph, which I think none of you have seen before. It was only released at the beginning of this month, at the beginning of July, and it shows the sun as a composite image from the last 183 days. And the black line, black dots you can see are the same sunspot, but a day apart. So it's actually a total of 183 photographs all combined together. And again, there's more details in the handout about this. So here's a historical record starting at 1600, more or less up to the current time. And a couple of important things to mention. 1600 was the time of Galileo and his run-in with the church, and Kepler and various other people. And during that century, 1600 to 1700, from a climate point of view, the important thing was the development of the thermometer. And one thing which this slide doesn't show, but in 1659, they started a temperature record using thermometers in central England, and that's now the longest running and considered reasonably accurate land-based temperature record for the last 365 years. Each of the spikes which you see in this particular chart is a solar cycle of 11 years. And the yellow ones, which are when the sun was hotter and working harder, and the red ones are when it was a bit cooler. This is what's called a proxy record. We think that it's the best way of figuring out how active the sun is. And what you should also look at is the blue line, which basically has a 100-year cycle itself. So it's low at 1700, low at 1800, 1900, it goes down, and it's come down over the last 4 or 5 cycles. So we're currently in cycle 25, that's an 11-year cycle. And if we go back to cycle 21, it goes down 22 and 23 and 24, they're all going downhill. And one of the slides I'll show you later shows that we did get to a completely spotless sun. So that's a historical record. It shows you that the sun isn't fixed. It cycles on and off during the years. During the minimum, it was so cold that people were skating on the River Thames and also on the canals of Amsterdam. And they had like a country fair, a frost fair, they call them, giving you some idea that what was going on at this time. Here's a different way of looking at the temperature record. And the organization called the IPCC, the International Panel on Climate Change, is a division of the UN, says, oh, there's been global warming and the temperature's gone up. And I entirely agree with them that if you look at this record over the last 170 years, there's definitely been warming. And the blue colors are obviously cooler, and the warm colors show that it's been getting warmer. And I'll show you later in this presentation that it's actually warmer than most people realize, and that we've broken the IPCC record. So anyway, there is a warm period that we've been in, but the problem with this particular slide is it only shows 170 years, and I'm going to show you the 2000-year record, where over on the right is the current 1850 to 2021 record. But there's a bigger and longer, hotter period called the medieval warm period. And way over on the left is the Roman warm period. And this is well known that the Romans thrived when it was a degree or two warmer. They built lots of fine roads and aqueducts and viaducts and lots of structures which has survived the 2 years. So there's a long periodicity of warm and cold periods, and going up 1 degree is not bad. I would argue that most people in Montreal would be quite happy if the winters were 1 degree warmer. Okay, we're just coming back to the sunspot diagram, and on the left is cycle 24, and on the right is cycle 25, and in between at 2020, literally the sunspots went down to 0. And I remember seeing pictures of the sun with not a single sunspot on them. So this has been going on. And I would think, looking at this diagram, that cycle 25 that we're in is just about the same, maybe slightly higher than cycle 24, and will be going downhill from here. So people watch these sunspots and also measure them on a daily basis and where they are. They're each given a name. This one's a much busier slide, and I'd like you to concentrate on the top left-hand corner where there's like a blue triangle and a black line on top of it. This is measuring the last 40 years of the CO2 levels. On the left, it's at 335 parts per million, so the units are ppm, and it's gone up about 80 parts per million. So over 40 years, that's 2 parts per million. If this was a class, I would ask the class, can you tell me why it's got a saw edge? It may not be obvious, but it turns out that we've had 40, 50, 60 years to look at it, and people are now quite sure why there is this saw edge to this graph. It's a little bit like the Latin American dance, a cha-cha. You go up 4 steps, cha-cha-cha-cha, down 2 steps, and you go up 4 steps and down 2 steps. And what's happening, they have done an attribution where they say that in the northern hemisphere is where 70% of the land is on planet Earth. And in the spring, when all the leaves come out, they suck up CO2. And the CO2 literally gets decreased during the spring and summer. It actually happens on a daily basis that the amount of CO2 in the air goes down during the day or during the spring and summer. And then in the winter, when nothing is growing much in the northern hemisphere, it actually goes up the 4 steps. And what this diagram is meant to show is at the bottom is the satellite temperature record from what's called UAH, the University of Alabama in Huntsville. And it's considered, without a doubt, the best temperature record available, but it only goes back to 1979, 45 years. And the message here is the top graph with the in blue and the black line is completely different from the one with the red line underneath. So there's no correlation between the steadily increasing carbon dioxide and the temperature record. And the red line has got spikes and valleys. And in this talk, I'll talk a little bit about the spikes and the valleys and what's caused that particular one. Over on the right is a more detailed graph, which I'll show you here. And I can tell you that in 2015, we had guests who came at Christmas time for some skiing, and it rained on Christmas Day in 2015. And the blue square is meant to be much further down, round about 1, and it went up to about 1.4. And that is the January record, which normally is the coldest month of the year, but not all in 2016. And the hottest time of the year is usually July, and typically they follow one another, the blue squares and the red dots. But in 2022, there's a big spike in the red dots. And so the question is, if it was a real class with people there, I would ask you, is that a real reading? Is it an error reading? Is it just within the margin of error? What happened in 2022 that all of a sudden there was this much warmer month altogether? And I might notice that the IPCC is interested in what they call the increase or the anomaly compared to the pre-industrial baseline temperature. So it took a hike up from about 1 to 1.4. And I can tell you that the UAH temperature record, the satellite record, is good to at least 1/10 of a degree. So I didn't think it was an outlier. And Doug Lightfoot and I have been looking at the data quite carefully, and we think the answer is on the other side of the world. So here we have Australia, New Zealand, and while I'm here, just point out the Philippines in the top left-hand corner. There was a major volcano there, and what we're going to talk about is volcanoes for 2 or 3 slides. The important thing that you should look at is where Tonga is, and I'd be interested in a show of hands as to how many people have even heard about Honga Tonga, which was what you call a volcano as well. And the thing that was exceptional is that this volcano was just at the optimum depth below the surface. So it was what they call a submarine volcano. And you'll see this down in the bottom right. It built up under the ocean, and it was about 500 feet below the surface and blew a huge amount of material, but mainly water vapor, into the air. And if you look at this particular slide, you can see that all the material that finished up actually went down with the to the west with the trade winds. And one of the times that the US government really worked quickly, down in the bottom left-hand corner, is a team that was put together within 1 week of the explosion, which was on the 15th of January. And a week later, on the 22nd of January, 22, the team from the US was sending up weather balloons, which is considered to be a really accurate way of measuring the data. And they did this every 6 hours for weeks at a time. And they got the chart, which is in the top left-hand corner. And from the chart, they could add up all the area underneath the blue line to the left and see that 146 million tons of water got blasted into the stratosphere. And so on the left is the altitude in kilometers, and it will just show you a little bit more of the different levels of the atmosphere. We all live at ground level in the lower troposphere. Most commercial planes fly at 10, 11, 12 kilometers, 35,000 feet, still within the troposphere. But all the water went up to where you see the red line, which is 60 kilometers high. So most of it went into the stratosphere and increased the amount of water vapor was there by 10% or more, enough to have a major impact. And it actually kept the heat into the lower areas. So over on the right is where this submarine volcano is. And this whole area is really pretty active. They talk about the ring of fire that includes volcanoes, which we haven't mentioned, Tambura, and also in the Philippines, there was this one called Pinatubo. And so this area is very active, and underneath the Pacific Ocean are sets of tectonic plates that move around, and that's where the El Niños start. So we'll show you this diagram, and over on the left, you still can see New Zealand and also Australia, and underneath the ocean is where there are deep volcanoes taking place, and they release a lot of hot magma, and that gets then comes to the surface as warm water and goes from the west to the east. So you get a flow of hot water that goes all the way up North America, all the way up to Alaska is a hot area, and down to South America as well. On the right is showing you the alternative. And by the way, there's a technical error in this slide, which I will ask my co-author to correct. The one on the left, the warm water goes from the west to the east. El Nino, which is a cold phase, goes from the east to the west. I think a couple of arrows would improve the diagram. But this warming and cooling is anywhere from 3 or 4 years up to 7 years altogether. So here, by the way, on the left shows you there's a source of heat that has nothing to do with the sun directly, nothing to do with CO2, but is a lot to do with the oceans and moving a huge amount of energy across the Pacific Ocean. Okay, so Here is the effects of the El Niños. You get more precipitation, especially on the west coast of the States and down in South America. You get droughts in Australia, and you get severe weather in North and South America. So in Canada, we have mild winters. I mentioned 2015 as well, when in the middle of the winter it started raining, which is unusual for us. And I'm sure some of you remember the ice storms, 1998. That was also an El Nino year. So it's amazing that an activity in the Western Pacific affects our weather in Eastern Canada. That shows you how important the oceans are for weather events. Okay, the research that we've done over the last 2 years is just shown in the top of the graph. The grand solar minimum started in 2020. 21, there was one reading that was a little bit high. In 2022, the next reading was much higher than expected, and it continued to go up. At the very top in the year, this year, 2024, there's a blue square, which is in and among the highs, completely out of place. I would expect it to be down at 1. And then the small red dots are the individual months, and you may have trouble seeing it, but April is off the chart, above the 2 level, right in where it says 2024. There's a red dot, which is April from this year. Then May it started coming down, June it started coming down, and I expect it to continue downhill back towards the 1.5 mark and even below that. There's a law or a concept by a French climatographer called Chantelier, which said that in general, in looking at weather, things will revert to the normal. So the normal parts were more or less the left-hand side of this chart. The right-hand side is completely outlier and different event, but it will revert back to the mean. As Rod said, I went to Glasgow University. The most famous person there was Lord Kelvin, and he said, all science is numbers. So here we've taken real observational data and we've plotted them for you. And based on this, we think that the El Nino was an important part of it. The Hunga Tonga volcano was very important, and the grand solar minimum. So 3 factors came together, but now they're pointing downhill. So that's what we mean about knowing the numbers and looking at it. And at the bottom right-hand corner, again, is that satellite record. And this shows the peak on the right, which is the largest peak in the last 45 years since they started it. So without a doubt, the temperature's been going up. And if somebody says that last year or this year is the warmest year ever, I'd agree with you over the last 50 years. That's the case. Okay, moving right along. This is the way the IPCC does its science. The IPCC is a governmental organization of 195 governments. They don't do any science directly. They accept reports, and in this particular one, it's looking at 32 countries' models. And these models are all the little sort of spaghetti lines, and the big thick red line is an average of 30 of them. I'm sorry to say that the hottest one is the Canadian one, and the lowest one is the Russian one, which is down at about the 0.4 level. The real observational data are the blue squares, which we showed you before, and the satellite records are in blue, and the balloon records are in green. And there's huge divergence between the two. So I don't think the red line is a correct line. I put my money on the series at the bottom, the blue and the green lines, as being real observational data. Here, just to make it look a little bit less mixed up, the blue line at the bottom, again, is the temperature record from the University of Alabama. And the blue and the red one is one from the British Research Center. And we can look at these, and the experts look at them and see, why was there a particular spike And we've shown a couple of El Nino ones there, including the 2015. And on the left is a downward, which could be a La Nina, but it's not. It was another volcano that put ash into the air. And so they look at these and try and figure out what's going on. One thing we can relate to is Montreal is on an island, and it's definitely causes to be warmer being in the middle of a city. So if you think of the island of Montreal, if you live out on the West Island or you live on the South Shore, you will know that it's cooler as you drive out of town. So I'm in the townships right now. I crossed the Champlain Bridge. It goes down by a degree or two. And by the time you're really in the country, after the end of the REM and Highway 30, you're down on the right of the chart. And if you have a look, there's a 3-degree difference in this diagram between being in the rural areas and being in the center of a city. So people know this, that the big cities distort the climate record altogether. You couldn't have a climate talk without talking about the polar vortex. And this is interesting that it's affected by the sun and the solar wind. And on the left, when there's a strong jet stream, they use the term zonal, but it goes round more or less where the Arctic Circle is, and just below that. And planes, when they fly to Europe, they go far north and join the jet stream, and it can take an hour off the flight to Europe if you get into the jet stream. Okay, so that's different. On the right is showing you what happens when the sun is weak, the solar wind is weak, you get this wavy meandering line, and that shows you how you get some pretty big variations. And when it's weak, the cold air comes in from the polar, and they talk about a polar outflow, and which side of the Arctic or the jet stream you're on makes a huge difference. This one gives you some idea that if you're growing trees or you have a vineyard, and if it's warm and then buds come out, and then there's a very cold period, which there has been for a couple of years, down to -30, then it kills off the buds from the spring and you lose a whole year of production. So that's one of the effects. The same thing happened to peach trees in Georgia. So it's this warm, cold, warm that comes from being on one side of the jet stream or another. Okay, so what's the difference between weather and climate? Climate is just arbitrarily defined by the World Meteorological Organization as 30 years. And one thing most people don't say, oh, it must be climate change. Well, there's many things that make up the climate. Is it the temperatures? Is it the rainfall, snowfall? Is it the amount of ice on Antarctica or Greenland? Each of these has a 30-year average. And the 30-year average by itself doesn't change the amount of snow in Greenland. It's a number, and there are many numbers in a climate record, but it's the variation of that that happens. And the temperature, I think, will be going down over the next few years, and that will change the climate readings. So the bottom of the slide says El Nino volcanoes are short-term, they're less than 30 years. The sun has long-term temperature changes, and the greenhouse gases are also long-term. The next slides I'll go through quickly. It's just showing you that there's not much change. This is tornadoes in the States, and you notice that if anything, they're going downhill over the last 70 years. Here, this is about cyclones. Again, there are some outliers, some strong ones, but over the last 50 years in this case, there's really not much change. This slide is what I call great news, is that it's produced by somebody, a Danish guy called Johan Lomberg, and he's gone through and over the last century looked at, are there climate-related deaths from floods, droughts, storms, wildfires? And most people don't know this, and you can read at the top, it says the deaths of the climbed by over 97% because we're richer, smarter, we have more cell phones, and we're more resistant, and we're better prepared to handle disasters. And from this graph, there's no sign of any major climate disaster. The weather's just sort of weather as usual. Yeah, it's going up or down a little bit. And this separates out whether it's from flooding or whether it's long-term changes. So Doug Lightfoot wanted to put this particular one in, which said that you should understand the IPCC position is not the same as our position. They think that the IPCC think that there's little or no warming from the sun on the Earth. We disagree, okay? The IPCC never mentions or has any comments on the satellite record that we have, and they produce a 40 or 50-page summary of their big reports, which are big fat documents, 3,000-4,000 pages long, and they never mention the satellite recording as if they didn't exist. And we might just mention why that's the case is that in the notes, it points out that the mandate of the IPCC is to only look for human induced climate warming. And they really aren't interested in the shorter term diagrams that I've shown you. So anyway, we think the sun impacts the temperature. There are long-term maximum and minimum. According to one of the people we work with, the grand solar minimum started in 2020. And things like the Gulf Stream, AMO is the Atlantic oscillation that's most likely going to get weaker and move into a cold period after 30 or 40 years. So the things that affect the temperature that we've looked at are volcanic action and specifically the oceans, El Nino and La Nina. The storms are not getting worse. There's no climate crisis as far as we're concerned. The number of climate-related deaths is certainly less than it was, gone down by 98% over a century. And the last line, we mentioned the four main greenhouse gases. The first one, H2O, is water and water vapor, CO2, methane, and nitrogen oxide. And water vapor is important. Everybody who's been to the tropics knows that it's hot and humid, and that has a big impact on the weather. The other ones are minor trace gases, much less than 1%, less than 0.1%. And really, when you come to measuring the climate impact in degrees centigrade, they're so small that they're immeasurable. You cannot detect CO2 temperature impact, which most people don't realize. This last photograph is a summary of our talk. We think the sun is the most important item. We think the ocean is the most important way of moderating the heat. It absorbs heat, it stores the heat, and it moves the heat around. And I haven't talked much about the clouds, but there's a new theory out just within the last year from a Nobel laureate, John Clauser, that says it acts as a thermostat. The clouds come up when it's getting too hot, and if you're in the shade, that goes down. So this is the last slide, and again, we think that the El Niños are going to go down and will actually become a La Nina in a few years. There's the grand solar minimum we've talked about. We're going to have the wobbly line on the vortex, polar vortex, and even the AMO is going into a cool phase. So our prediction is not for global warming, it's for temperatures coming down over the next 2, 3, 4 decades altogether. So that's the end of the talk. I think we did it in very close to 30 minutes. And if you have any questions, I will take them now as long as Malcolm and Tony are happy with that. But if you want to send me questions, I will answer them by email as well. So I'm going to stop sharing my screen, and you're welcome to ask questions.
I'd like to start, if I may.
So can we have somebody thank our speaker?
I'm going to do that right now, I think.
Thank you very much.
The amount of data there obviously is a lot for us mere humans to,
Right.
us mere mortals to handle. But I'm just really impressed with the way you've stuck to the numbers as you see them, and are making a statement that a lot of people might refute. But it's nice to see a presentation that is backed by numbers, that has a really solid scientific background behind it. And if I may add, very, very well presented. I'd like, on behalf of us all, I'd like to thank you very, very much, Gerald.
Jim, could I just add that what I presented is not a technical paper. There's no references, but there are 2 links to 2 of our papers. And if you want to dig deeper, you look at those. They're in the handout. They're not in the slides. And, you know, we are members of what's called Clintel, where there's 2,000 people like ourselves who have a similar background, similar point of view.
Thank you very much. Yeah, and we have access to that information.
Yes, it's in the handout. If you have the handout,
Okay, great.
Did you send out the?
Yes, we got it yesterday.
Okay, so at the end of where is it? At the end of slide 29, down here on this page are 2 links, and they will give you the latest papers. And I can tell you the basic concept that we have is to collect real data, and we actually use a cell phone. This is my co-author's idea. You use your cell phone, and there are close to 1 million weather stations in the world. And then you can go and read the temperature and the humidity. And with that, you can do the analysis that we did. But we collect the data. We're not using any models. We're not even using the IPCC data. We're collecting real new data. And we've done this over the last 2 or 3 years. And the latest paper, we collected data just a few months ago.
Excellent. Thank you very much again. Much appreciated.
That, by the way, is the concept of the scientific method. You have an idea and you test it with real data.